Deep learning with artificial neural networks, ANNs, is a fascinating and powerful approach within the field of artificial intelligence, AI. Let's dive into a comprehensive overview of this topic. Deep learning refers to the use of neural networks with multiple layers to process and learn from complex data. ANNs are computational models inspired by the structure and functioning of the human brain. They consist of interconnected nodes, or artificial neurons, organized into layers. Each node takes input, performs a calculation, and passes the output to the next layer. Here are the key components and concepts related to deep learning with ANNs. 1. Neural network architecture. The architecture of a neural network defines its structure and organization of layers. Common architectures include feed-forward neural networks, convolutional neural networks, CNNs, for image processing, and recurrent neural networks, RNNs, for sequential data. 2. Layers. Neural networks comprise input, hidden, and output layers. The input layer receives raw data, while hidden layers process and extract features from the input. The output layer produces the final result, such as a classification or prediction. 3. Activation functions. Activation functions introduce nonlinearities to the neural network, enabling it to model complex relationships in the data. Common activation functions include sigmoid, tan, and ReLU, rectified linear unit. 4. Backpropagation. Backpropagation is a fundamental algorithm used to train neural networks. It involves calculating the gradient of the network's error with respect to its weights and adjusting the weights accordingly, iteratively improving the network's performance. 5. Training data and labels. Deep learning models require a large amount of labeled training data to learn patterns and make accurate predictions. The training data consists of input samples, and the corresponding labels provide the desired outputs. 6. Loss functions. Loss functions measure the discrepancy between the predicted output of the neural network and the true label. They guide the learning process by quantifying the network's performance and providing an error signal for backpropagation. 7. Optimization algorithms. Optimization algorithms, such as stochastic gradient descent, SGD, and its variants, are used to update the weights of the neural network during training. These algorithms aim to find the optimal set of weights that minimize the loss function. 8. Overfitting and regularization. Overfitting occurs when a neural network becomes too specialized to the training data and performs poorly on new, unseen data. Regularization techniques, like dropout and weight decay, help prevent overfitting and improve generalization. 9. Pre-trained models and transfer learning. Pre-trained models are neural networks trained on large-scale datasets for a specific task, such as image classification. Transfer learning leverages these pre-trained models by fine-tuning them on smaller, task-specific datasets, saving time and computational resources. 10. Applications. Deep learning with ANNs has revolutionized various fields. It is used for image and speech recognition, natural language processing, autonomous vehicles, recommender systems, financial forecasting, and many other tasks that require complex pattern recognition and decision-making. It's important to note that deep learning with ANNs requires significant computational resources, including powerful hardware, example, GPUs, and large amounts of data. Additionally, hyperparameter tuning, model selection, and careful analysis of results are essential for successful implementation. Deep learning with ANNs holds immense potential, and ongoing research continues to advance the field, pushing the boundaries of what can be achieved in AI.